this is the n queens problem. Suppose we have a n by n chessboard and we want to put some queens on these chessboard without attacking each other, and we want to maximize the number of queens that we put on this chessboard. Okay, so suppose we want to start this problem, and for solving that we need to use some binary variables. So uij will tell us if a queen exists on the cell I and j. I is representing rows and j is representing column. Okay, and we want to maximize this summation. Okay, so some rules. On each column, for every given column, for every j, we can't have more than one queen on the board. So this is written as follows. So the summation over I over the rows should be less than 1. And also the same kind of similar constraint is here for every given row. The summation over j or over the columns should give us less than 1 queen on each row. Okay, this is another rule, chess rule. And the other rule is the diagonal rules. So it means that on every diagonal or anti-diagonal we can't have more than one queen. On some diagonals we can have no queen as well. Okay, so we want to solve this optimization problem in a way that these 4 constraints are satisfied. So there is an objective function, and for every j this constraint should satisfy, every I this constraint should satisfy, for every I and j if they are diagonal or off diagonal, these constraints should be satisfied. Okay, so let's have a look at the Python code developed for this purpose. Just a second. Okay, so this is the Python code. Okay, so first of all I have to import the required packages like Pyomo and Matplotlib, because at the end I want to plot the results, and also I have to specify what is the dimension of the board. So I specify this like that, and I have defined it mutable because maybe I need to change the size of the board, and also I is representing the set of rows, sorry, and j is the set of columns. But since they have the same number of cells, then I have defined them as alias. And model.u is a variable, is a binary variable representing if queen exists in that cell or not, and I have initialized that with 1. Okay, and we have 2 rules, one for row, one for column. So the summation of model.u ij for every j in model j should be less than equal to 1, and this row is defined over every I. Okay, for a given I, that summation should be valid. And the same a similar concept is for every column. So for every column j, summation over I should be less than 1. Okay, these 2 rules. And the other 2 rules are representing the diagonal and anti-diagonal set of rules. Okay, so model.cdiag1 is here, and it is represented over I and j, but not for every I and j. Those I and j that satisfy this specific relation. Okay, and this specific relation is representing the other diagonal of the board. Okay, and the objective function is defined as the summation of the uij for every I and j in the model, and the sense is the maximization. Okay, I run this cell, and then I specify the value of n. How many cells do we have on our chessboard? On each side of chessboard we can have bigger chessboards, and then try to solve it. I solve this problem and show you the results. So you can see here that these are the locations of the queens on the board. So here we have only one queen on this row, one queen on this column, one queen on this row, and one queen on this column, and the final tab will save that figure as a PNG file in your directory. Okay, so I can test it for a bigger kind of chessboard, let's say 16. Okay, and if I plot it, you can see here that this is the new kind of allocation of the queens. Thank you very much.